In the early hours of December 2nd, 2025, NASA confirmed something no one was ready to say out loud. The real size of 3I-ATLAS, the mysterious interstellar object, was not just larger than previously estimated, it was engineered. The calculations were right, the observations aligned, and the implications are now unavoidable. Because if this thing isn't natural, if its shape, structure, and thermal behaviour all point to the same conclusion, then everything changes. This episode isn't about theories anymore, it's about confirmations, and what NASA just admitted, silently but undeniably, shifts 3I-ATLAS from anomaly to active system, from comet to craft. Let's walk through the full data chain, because what they just revealed isn't speculation, it's measurement, and the numbers don't lie. It happened just after sunrise on December 2nd. Inside a quiet lab at NASA's Goddard Space Flight Center, a minor update was pushed to an internal dashboard, one that listed revised physical parameters for 3I-ATLAS. The update was routine, at least on the surface. A new thermal profile, adjusted reflectivity index, and a fresh size estimate based on combined data from JWST, SOHO, and the European Southern Observatory. But what triggered the alert wasn't the update itself, it was the number. The revised size of 3I-ATLAS was listed as 211 metres, with an error margin of less than 2%. Until that point, estimates had ranged from 60 to 110 metres. The object had always been difficult to classify due to its unusually low albedo and its chaotic brightness variations. But this measurement didn't just double the size, it transformed the object entirely. Because in astrophysics, size isn't just about scale, it's about behaviour. A natural comet that large should behave like one. It should eject measurable plumes of gas and debris under solar heating. It should develop chaotic asymmetrical jets, a rotating coma, and an expanding tail. But 3I-ATLAS didn't do any of those things. Instead, it stabilised. That's what made the December 2nd breakthrough so seismic. The size confirmation didn't explain the anomaly, it amplified it. The measurement came from an unusual combination: infrared shadow modelling, ionosphere reflectivity data, and synchronized amplitude resonance across multiple telescopes. JWST had been collecting high-resolution IR scans for several days, but it was the thermal breathing rhythm, a pulsing emission that seemed to circulate heat in cycles, that finally gave analysts a reliable read. In simple terms, the pulses weren't random. They followed a strict timing loop, and embedded in that loop was a consistent thermal delay, a lag between surface cooling and internal rewarming. By modelling that delay using known radiation propagation curves, the team was able to estimate how far energy was travelling inside the object before re-emerging. That internal delay corresponded exactly to a structural dimension of 211 metres across. The math was clean, the physics not so much. Natural comets don't regulate their own internal heat flow, they don't emit coherent pulses, they don't maintain structure under rotational pressure, and they certainly don't respond to solar radiation by cooling instead of heating. But 3I-ATLAS did, repeatedly, and now there was a number to match it. What followed inside the agency was silence, not confusion, but controlled containment. The measurement didn't need interpretation, it was engineering grade. It had error bars that would be acceptable in aerospace design, and that raised a deeper question. How does an object over 200 metres wide maintain perfect emission symmetry without breaking apart? The revised profile also forced re-evaluation of previous data. If 3I-ATLAS had been this large all along, then its apparent brightness was artificially muted. That meant either the surface was deliberately non-reflective, like stealth material, or the light was being emitted in a narrow spectrum undetectable to standard filters. Suddenly, the object's pulse signatures, its heat inversions, its near-perfect 3:21 harmonic ratios, they all took on new meaning. They weren't quirks, they were hints of internal architecture. And for the first time since its discovery, 3I-ATLAS couldn't be dismissed as just an odd comet. The measurement forced a choice: either accept a natural object with impossible behaviour, or acknowledge that we're seeing something built, something that functions, that measures itself, that adjusts in real time. That number, 211 metres away, changed everything, because it wasn't just a measurement, it was proof of structure, and structure means design. NASA never made an official press release. There was no televised announcement, No front-page headlines, no tweet from the administrator's account. But the confirmation, the one that changed the tone of every internal conversation, was right there, quietly embedded in a public-facing data log uploaded to a subdirectory on NASA's planetary data system at 0412 UTC on December 2nd. Most people never saw it. Most never would. Because unless you were actively monitoring thermal anomaly records and cometary motion residuals in cross-observatory feeds, the update looked like nothing more than routine telemetry. Just a series of numbers, timestamps, revised dimensions, a spectral index note. But to the analysts who'd been following the object since late October, to the researchers at ESA, JAXA, Harvard Smithsonian and even private observatories, that line of code wasn't just a new entry. It was the first confirmation. Not speculation, not modelling, not projection. Confirmation that 3I-ATLAS was no longer within the margins of natural variance. It had officially exceeded the bounds of known cometary behaviour. The dataset was labelled Thermal Profile, a 3-ATLAS v31.json. Inside it, an updated size. Parameter, just over 211 metres, with synchronised thermal drop pattern timestamps matching both JWST infrared readings and SOHO ultraviolet reflectivity analysis. But what stood out most was a 3-letter tag appended to the metadata. ARC. That tag stands for Artificial Reflective Control, a rarely used internal designation that flags objects exhibiting structured emission symmetry or non-random reflectivity profiles under solar exposure. It's a tag usually reserved for defunct satellites, controlled probes, or deep space remnants showing engineered behaviour. And now it had been quietly appended to 3I-ATLAS. No context, no explanation, no alarm bells, just a subtle classification change. But one that rewrote everything. Because the ARC tag is not applied lightly. Its presence means that analysts inside the agency had reviewed the data and agreed, at least privately, that the object demonstrated non-random energy modulation under varying light conditions. And not just once, but across multiple observational windows. In other words, someone inside NASA had seen the same pattern repeat again and again, and recognised it not as coincidence, but as response. That response came into clearer focus when researchers noticed something deeper buried in the logs. A timestamp match between 3I-ATLAS's brightness pulse and Earth-based reflectivity distortion, separated by 1.3 seconds, but repeating precisely in a way that mirrored Earth's rotational alignment. A 1.3 second delay might seem trivial, but not when it's consistent across multiple observatories from different continents. Not when it appears again in magnetospheric echo data, and not when it lines up exactly with the time light takes to travel from the object's location to Earth's upper atmosphere. Those who dug into the log's harmonic analysis data found a stunning pattern. The signal wasn't just structured, it was phase stabilized like an oscillator locked into sync. The same pattern that would appear in a feedback loop or a beacon. And yet still, there was no statement. Why? Because acknowledging it publicly would force questions NASA didn't want to answer. At least not yet. Was it natural? Artificial? Who or what was controlling it, if anything? The agency didn't say. Instead, they buried the ARC tag deep in metadata, filed under routine revisions, a document intended for data scientists, not the public. But those 3 letters were louder than any press release, and for those who knew what they meant, the message was deafening. This was no longer just a comet. Once the real size of 3I-ATLAS was confirmed, over 200 metres across, a new problem emerged. Not one of shape or motion, but of light. Because with that scale, the object should have emitted a predictable amount of thermal radiation, the kind of infrared glow we'd expect from any large sunlit body in space. Instead, what we got was a contradiction that shook thermal modelling to its core. The problem was first noticed by NASA's infrared spectrometry team cross-referencing data from the James Webb Space Telescope with readings from Solar Orbiter and SOHO. JWST had locked onto the object during its now documented 9-minute pulse cycle. Analysts expected some thermal oscillation, maybe minor cooling as sunlight faded, or heating as the object spun towards solar exposure. But that's not what they saw. Instead, they found that 3I-ATLAS cooled during peak brightness, and heated up again during relative dimming. This inverted thermal profile didn't make sense. In the physical universe we understand, brightness and heat go hand in hand. A hotter object shines more, a cooler object dims. It's governed by the Stefan-Boltzmann law, a cornerstone of black body physics. But 3I-ATLAS ignored this law entirely. The more it glowed, the colder it became. The colder it became, the more symmetric and bright the emissions became in the visible spectrum. This wasn't just strange, it was mechanically backwards. At first, teams suspected instrumentation failure, a miscalibrated sensor on JWST perhaps. But then ESA's solar orbiter confirmed the same anomaly using completely independent equipment. When the object pulsed with maximum light, its infrared profile dropped sharply, showing a loss of surface heat that was inconsistent with passive solar behaviour. To make matters worse, the UV sensors on SOHO and MAVEN showed a corresponding spike, indicating that high-frequency light was increasing during those thermal drops. In simpler terms, while the object cooled in the infrared, it became hotter in ultraviolet output. No natural comet had ever shown this kind of energy bifurcation. Researchers called this divergence the thermal inversion envelope. It marked the first time an interstellar object had demonstrated anti-correlated energy behaviour, where two wavelengths evolved in opposing directions on a strict schedule and across a known surface area. And that last detail, the surface area, was the nail in the coffin. Because now, with the confirmed size of over 200 metres, the energy calculations could no longer be hand-waved away. The object had a large enough surface that any change in heat or brightness carried measurable physical consequences, and yet it behaved as if some internal system was rerouting energy, suppressing heat emission while radiating focused light, as if it had a way to move energy internally and selectively expel it in specific wavelengths. More worrying was the consistency. The divergence curve was not noisy, it was smooth, predictable, phase-aligned with the 9-minute pulse. Every time the object flashed in brightness, thermal output dipped. Every time it dimmed, temperature returned. If it had happened once, it could have been dismissed. Twice, maybe a coincidence, but dozens of cycles, across different observatories, with synchronized readings, that's not a glitch, that's a mechanism. This forced one conclusion into focus. 3I-ATLAS is not radiating energy randomly. It's not behaving like a comet, an asteroid, or any naturally tumbling body. It is behaving like a controlled emitter. Some speculated that the object might be using its internal mass, or surrounding plasma shell, to store heat and discharge light in regulated packets. Others wondered if it was deliberately masking its thermal profile, like stealth aircraft on Earth designed to evade infrared detection. Whatever the mechanism, one fact held, the size didn't match the light. And in that mismatch, a new question appeared. What kind of object knows how to hide its own heat? Once NASA confirmed that 3I-ATLAS measured over 200 metres in diameter, expectations across the scientific community shifted. A body of that size should behave like a massive, gravitationally obedient object. It should have momentum, inertia, resistance to sudden motion changes, but that's not what astronomers observed. Instead, 3I-ATLAS continued to do something that no object its size should be able to do. It manoeuvred like it had no mass at all. At first glance, the orbital path looked normal, a hyperbolic trajectory, fast and steep, consistent with interstellar origin. But when teams began comparing the precise motion vectors across time, especially during its closest solar approach in late November, they noticed an unsettling pattern. The object wasn't just drifting through the solar system, it was adjusting, and it was doing so with a responsiveness that defied basic physics. The first clue came from a set of positional anomalies detected by the Very Large Telescope Array in Chile. Across 3 consecutive nights, the object's position deviated from expected models. Not by much, but by just enough to trigger a recalibration. Initially assumed to be a data processing error, the anomaly was confirmed independently by Japan's Subaru telescope, and again by ESA's Gaia tracking network. When the deviations were plotted together, they formed a consistent arc, subtle, deliberate shifts in trajectory, as if the object was ever so slightly curving its path toward quieter regions of solar wind. These weren't course corrections we'd expect from outgassing jets or solar radiation pressure. These were vector-controlled maneuvers. That kind of adjustment requires one thing: feedback. The object appeared to be sensing its environment and responding in real time. But what made the discovery even more confounding was the speed. Based on its size and the estimated mass of a 200-metre interstellar object, any motion change should have required immense force, something visible, energetic, and accompanied by clear debris or ejection trails. Yet no such force was observed. There were no dust plumes, no outgassing jets, no thermal recoil, just a change in direction and silence. NASA's propulsion analysts calculated the energy needed to produce those shifts. Assuming conservative mass estimates, the force-to-acceleration ratio suggested a mass efficiency far beyond known natural processes. In effect, the object behaved as though it had significantly less inertia than its size would imply, as though it was built from a material or field structure that minimized momentum. In theoretical physics, this is sometimes described in terms of inertial dampening, a concept more familiar in science fiction than astrophysics. But with 3I-ATLAS, it wasn't theory, it was happening. Further data came from the Parker Solar Probe, which had passed through overlapping regions of plasma near the object's trajectory. Parker detected minute fluctuations in solar wind density, slight pressure waves that seemed to originate near 3I-ATLAS. The waves were timed precisely with each 9-minute pulse, and each time a pulse occurred, the object's path shifted ever so slightly. That pulse-to-motion relationship is impossible to ignore. It's as if 3I-ATLAS was shedding massless momentum, using some internal oscillation to push itself subtly through space, a technique similar to the concept of reactionless drives. Again, nothing about this is supposed to happen in a natural object. Comets don't pulse, they don't react, and they certainly don't move without mass loss. So how does something this large, a body the size of a high-rise building, move as though it weighs nothing? Either our understanding of momentum is incomplete, or this object is using a propulsion system we don't yet understand. One that doesn't push off dust or gas, but pushes off space itself. And that changes everything. By late November, observatories around the world had started to whisper the same thing. They weren't seeing random fluctuations in 3I-ATLAS's brightness. They were seeing rhythm. From Chile to Hawaii, from orbital satellites to backyard telescopes, the data was beginning to align. The light coming off the object wasn't constant, and it wasn't chaotic either. It was pulsing, brightening and dimming with mathematical regularity. At first, no one wanted to say it out loud. A comet, especially one on an interstellar trajectory, isn't supposed to blink like a beacon. But once the datasets were overlaid, the pattern was unmistakable. Exactly every 9 minutes, the object emitted a soft but detectable increase in brightness. It wasn't a flash. It wasn't a flare. It was a smooth, deliberate climb followed by a gentle drop, a pulse. And it happened across all instruments, all platforms, with a margin of error that stunned even the most skeptical analysts. This wasn't just a light curve, it was synchronized emission. The breakthrough came when the Mount Stromlo Observatory in Australia compared its pulse detection timestamps with those from the Keck Observatory in Hawaii. Despite the telescopes being nearly on opposite sides of the planet, with different angles, weather and instrumentation, the pulses were detected at the exact same global moment. Not a second off, not even milliseconds. That kind of synchronicity ruled out atmospheric effects, viewing angles and signal lag. It pointed to a single conclusion. The pulse was originating from the object itself, and it was coherent across vast distances. But what caused it? Comets do not pulse. Some exhibit erratic jets or spinning dust ejections, but those are unpredictable. They vary with solar heating, surface composition, and chaotic rotation. They do not repeat on a precise interval, and certainly not with a clock-like precision. The 9-minute pulse of 3I-ATLAS was tight, within a window of 0.02 seconds across dozens of observation points. It was as if the object was operating on its own internal metronome, something cycling, something regulated. NASA and ESA ran Fourier analyses on the pulse data. What they found shocked them. Each pulse contained 3 distinct harmonic layers, frequencies nested inside one another, with peak amplitudes appearing in ratios of a 1.24. This wasn't just a periodic fluctuation, it was structured modulation, like a carrier wave encoding information. In audio terms, it resembled amplitude modulation, AM radio scaled to the interstellar level. That changed the conversation completely. Now scientists weren't just asking if the object was pulsing, they were asking if it was broadcasting. There was more. Every time the object pulsed, Earth's ionosphere responded. observatories in Canada and South America recorded faint electromagnetic echoes precisely 1.3 seconds after each pulse, the exact delay expected from light-speed travel at that distance. These reflections weren't noise, they were narrow band, aligned to the same frequency envelope as the visual emission. The implication was staggering. This object was not just emitting light on a timer, it was emitting light that Earth's atmosphere could resonate with. And the pulses were so consistent, so stable, that they triggered recalibrations in several radio telescopes that assumed their timing systems were off, because nothing in space is that regular, unless it's designed to be. There are only a few natural objects in the universe known to pulse at regular intervals. Pulsars, spinning neutron stars, and certain binary systems, but those are massive, magnetic, and emit in radio or X-ray bands. 3I-ATLAS is none of those things. It pulses invisible light, every 9 minutes, exactly, like a heartbeat, like a system that's alive, or worse, one that's measuring time. If the 9-minute pulses of 3I-ATLAS had been confined to deep space, they might have remained just another astrophysical curiosity. Something strange, yes, but distant, harmless. However, in the early hours of November 30th, researchers began to notice something that shattered that boundary completely. The pulses were showing up here, not just in telescopes, not just in light curves, but in Earth's ionosphere. At first, it was an odd signal, a tiny narrow-band disturbance logged by the Canadian Hydrogen Observatory. It appeared in the VLF, very low frequency, monitoring band, usually reserved for tracking lightning strikes, solar flare echoes, and auroral currents. But this wasn't terrestrial, and it wasn't solar. The anomaly repeated every 9 minutes, precisely, quietly, and then it repeated again and again. Within hours, other observatories joined the list: the Arecibo Successor Array, the South African National Space Agency, and independent ham radio operators tracking ionospheric bounce patterns across the globe. They all reported the same thing: high-altitude reflection distortions coinciding with 3I-ATLAS's optical pulses. But here's where it became undeniable. Each ionospheric reflection occurred 1.3 seconds after the visual pulse had been recorded by ground-based telescopes. That's the exact time it takes for light, or any electromagnetic radiation, to travel from the current position of 3I-ATLAS to the upper atmosphere of Earth. This wasn't a coincidence. This wasn't local interference. This was real-time response. Something emitted from 3I-ATLAS was interacting with the upper layers of our atmosphere, and it was doing so with surgical precision. The phenomenon was subtle. It wasn't loud or destructive. No satellites were disrupted. No GPS systems failed. But to scientists who specialize in ionospheric science, the implications were stunning. These reflections were not broad scatterings like auroral discharges or solar flare echoes. They were tightly modulated, narrow in both frequency and spatial spread. The signal's coherence meant it retained its structure even after crossing tens of millions of kilometers of space. The leading theory was that the pulses, originally detected in visible light, carried embedded electromagnetic harmonics. In other words, they weren't just light. They were encoded structures riding on that light, and those structures were complex enough to refract and bounce off the ionosphere in patterns usually only seen with intelligently crafted radio bursts. Scientists at CERN's Data Synchronization Division were called in to investigate the pattern. They ran phase alignment checks using the same algorithms used to detect ultra-faint signals from deep space probes. The signal coming from 3I-ATLAS passed those tests. It had coherence, not just brightness, not just timing, coherence, the hallmark of signal architecture. Even more shocking, the reflection strength varied slightly based on Earth's rotational position. When the ionosphere's density was at its peak over equatorial regions, the reflections became stronger and more defined, indicating that 3I-ATLAS's emissions were not only reaching Earth, but doing so in a way that interacted with Earth's atmospheric composition itself. In simpler terms, the object knew where we were, and more, disturbingly, it seemed to anticipate how to reach us. That's not what comets do. Comets don't calculate. They don't align their emissions with planetary fields, and they certainly don't ping our ionosphere with a regular pulse that travels the distance between stars with zero dispersion. Several research teams proposed that the reflections might be accidental, the byproduct of some unknown plasma interaction near the object's core. But the precision undercut that idea. The signal was targeted. Not in the sense of aggression, but in intentionality. It wasn't noise, it was a handshake, and Earth had just responded. Thermal equilibrium is one of the most fundamental principles in astrophysics. When an object is exposed to sunlight, it absorbs energy. That energy must go somewhere. Some of it reflects as visible light, but the rest becomes heat, infrared radiation, radiating outward from the surface. The bigger and brighter the object, the hotter it gets. This is true for everything from asteroids to stars, but for 3I-ATLAS that rule simply does not apply. In the days following the confirmed 211-metre size estimate, researchers expected that the object's thermal signature would finally align with its physical scale. Larger surface area meant more exposure to sunlight. More exposure meant more heating, and with that much mass, even a low albedo object should exhibit a measurable increase in core temperature. Instead, what came back from the James Webb Space Telescope was an unmistakable absence. The core of 3I-ATLAS remained cold, even during peak energy output. Infrared spectrometry performed over multiple orbits showed consistent thermal readings well below what was predicted. During the object's rhythmic 9-minute brightness pulses, the expectation was that core temperature would spike briefly as energy radiated outward. But the opposite occurred. The object brightened and cooled. At first, this was dismissed as a sensor issue. Webb's NearSpec instrument team rechecked the calibration logs, suspecting a faulty baseline or an overcompensating temperature correction algorithm. But parallel readings from ESA's solar orbiter and data from NASA's MAVEN probe confirmed the same thing. Every time 3I-ATLAS emitted its synchronized optical pulse, its thermal output dropped. This phenomenon, cold emission during radiative peaks, has no natural analogue. The closest comparison in terrestrial terms would be a laser cavity, where specific wavelengths are amplified and emitted while internal heat is suppressed by reflective chamber design. But lasers are constructed, deliberately. They are machines that channel energy into directed output, suppressing entropy and retaining internal stability. What made the readings even more unsettling was that the temperature drop occurred only in the core, not the surrounding halo. While the central body cooled during each pulse, the outer atmosphere or coma showed slight thermal turbulence. The heat was moving outward, yes, but it was doing so in a patterned wave, not diffusion, not convection, something else, something coordinated. This data directly contradicted the expectations laid out in the thermal models of cometary activity. Normally, when a comet brightens, it is because sunlight causes surface ices to sublimate, changing from solid to gas and releasing energy in the process. The byproduct is heat, jetting, asymmetry. But 3I-ATLAS showed none of that. There were no visible plumes, no detectable gas emissions, and no rise in thermal radiation even during its most luminous cycles. The heat curve stayed flat, or worse, it dipped. This led to a new line of inquiry. Was 3I-ATLAS absorbing heat at all, or was it actively redirecting it? Using multispectrum overlays, researchers created a composite thermal map that showed the distribution of energy across the surface. What they found was remarkable. The areas of brightest visible light were consistently the coldest, and the zones that absorbed the most solar radiation, based on incident angle, didn't heat up at all. The core wasn't reacting to sunlight the way rock or ice should. It was behaving more like a thermal insulator, or more precisely, like an energy routing system, one that deliberately moved heat away from the source of radiation and out toward its outer shell. To do that, the object would need structure, not loose rubble, not chaotic ice, but channels, conduits, a thermal framework. In other words, 3I-ATLAS wasn't heating up because it was choosing not to, and that made the scientific community pause, because only engineered systems can control heat like that. And this one just might be running cold by design. In the controlled silence of the European Space Agency's Deep Space Operations Centre, something happened that no one could explain, at least not immediately. On the morning of November 28th, a new data batch from multiple observatories fed into ESA's synchronization matrix. It was standard procedure. Every few hours, signals from telescopes around the world are time-matched to identify inconsistencies in cosmic event logging. But this time, the system didn't flag a delay. It flagged perfect timing, and that wasn't supposed to happen. The event became known internally as the clock event. What it revealed didn't just reshape our understanding of 3I-ATLAS, it gave researchers an entirely new way to measure it, not by looking at the object, but by analysing how it interacts with time itself. Here's what happened. During one of 3I-ATLAS's 9-minute light pulses, 17 different observatories, including the European Southern Observatory, La Palma and Cala Alto, recorded the peak brightness at the exact same universal time, UTC 03:41:27:092, to the millisecond. Across different continents, under different atmospheric conditions with different instruments, that level of synchronization is unheard of in astrophysics. Normally, light signals, even those moving at light speed, arrive slightly staggered due to Earth's curvature, atmospheric density and instrumentation lag. Even with GPS-calibrated atomic clocks, a natural light source will still produce minor discrepancies in timestamp alignment. But not this time. ESA analysts ran correlation checks against internal timing data and external backups. Then they checked against air-gapped observatories, systems not even connected to the internet, and found the same timestamp. This event was global, and it was clean. It raised a difficult question. How could an interstellar object emit a pulse that arrives at all points on Earth with no detectable time variation? To achieve this, the object would need to pre-adjust the emission. It would have to know in advance the distance and light travel time to every observatory watching it, compensating for Earth's rotation, curvature, and orbital velocity. That requires computation, and not just any computation, it demands real-time geospatial modelling, which no natural object should be capable of. But it also allowed for something no one expected: dimensional inference. ESA scientists realised that if 3I-ATLAS could synchronise emission to match light arrival on Earth, then embedded in that signal must be a structure, a delay pattern that reflects the time it takes light to traverse internal distances before being emitted. In simple terms, if the light wasn't coming from a single point but instead from a structured surface, like a shell, then the microdelays in internal modulation could be used to estimate the object's physical size. So they ran the math. By analysing slight harmonic dephasing in the early leading edge of the pulse, they detected what's known as a multi-node oscillation, a set of concentric modulation patterns that only occur in physically extended, synchronized systems, like sonar pings inside a hollow structure. When modelled against known waveforms and compared with the previous thermal breathing delays, the harmonic intervals pointed to one thing: a diameter of approximately 211 metres, with a tolerance of less than +3 metres. That number matched the thermal transport model from JWST exactly. 2 different measurements, 2 different instruments, 2 different phenomena, same result. Suddenly the clock event wasn't just a mystery, it was a measurement tool, and what it measured was chilling. This object wasn't emitting random energy, it was pulsing in structured patterns, not just in brightness, but in time, and the only way it could be doing that is if it had internal architecture capable of producing synchronized, dimensionally stable outputs. The timing wasn't an accident, it was a signature, and for the scientists reviewing the data, that's when they knew. 3I-ATLAS wasn't just moving through space, it was interacting with it, deliberately. For decades, comets have been observed as chaotic, often beautiful messes. Their comas shimmer with dusty diffusion, and their tails stretch unevenly, sculpted by the violence of solar radiation. Edges blur, brightness fades outward in gradients. That's how natural bodies behave, especially those shedding volatile compounds under heat stress. But 3I-ATLAS refuses to behave naturally, and on the night of November 30th, observatories equipped with adaptive optic systems recorded something that most astronomers never thought they would see from a so-called comet: sharpness. Not just clarity, not focus, edges. At the Keck Observatory in Hawaii, engineers operating the twin 10-metre telescopes noticed an anomaly in the live feed. The object wasn't just unusually bright, it appeared to hold its shape under magnification. While most comets blur into fuzzy halos with increasing zoom, 3I-ATLAS displayed a defined perimeter. A luminous shell, yes, but one with abrupt fall-off, a hard boundary where the glow simply stopped. This was confirmed again the following night by La Palma's Gran Telescopio Canarias, using state-of-the-art adaptive optics that correct for atmospheric distortion in real time. Their data reinforced the same disturbing observation. The glow surrounding 3I-ATLAS wasn't diffusing naturally. It looked contained, and more than that, it was symmetrical. The object did not present the messy, asymmetrical emission cloud typical of icy bodies under solar stress. There were no jet trails, no gas streamers. Instead, the glow formed a consistent radial shell. It didn't stretch in the direction of solar wind. It didn't tail away from the sun. It sat like a self-contained luminous sphere, pulsing gently, surrounded by what some observers began to call a light envelope. This envelope didn't behave like a coma. It had no turbulence, no expanding gradient. When brightness levels were plotted frame by frame during the 9-minute pulse cycle, analysts noticed something subtle but precise. The diameter of the light shell expanded and contracted ever so slightly in time with the pulse rhythm. Less than 1% total fluctuation, but measurable. The sphere wasn't static, it was breathing. That term, breathing, spread quickly through internal reports. It's not meant literally, of course, but the motion had that quality, a slow, deliberate expansion and contraction, as if the glow itself was controlled, projected. Now here's where it gets stranger. Under deeper analysis, the outer edge of the glow wasn't just a brightness cutoff. It exhibited a gradient inversion, a point at which the intensity suddenly dipped, then spiked outward before vanishing completely. In optics, this is known as an edge reinforcement signature, typically seen in lensed systems, where light is directed through boundary fields or reflective cavities. In other words, it didn't just glow outward. It looked like it was being shaped, possibly even refracted. This created a whole new wave of speculation. If 3I-ATLAS's glow was being shaped, not emitted freely, then some form of field containment might be in play. Not magnetic in the classical sense. No corresponding charged particle flux was detected. But perhaps electro-optical modulation, or even something exotic like plasma lensing. Several astrophysicists suggested the possibility that the visible glow wasn't the primary emission at all, but a byproduct, a projection, the skin of something hidden beneath. And if that's the case, it raises a terrifying possibility. What we're seeing isn't the object. We're seeing what it wants us to see. The sharpness of the glow, the lack of diffusion, the spherical uniformity, all of it defies cometary physics. This wasn't solar radiation bouncing off dust. This wasn't ice turning to gas. This was something more deliberate, something controlled. And through the most advanced lenses humanity has ever built, we may have finally seen it for what it is. Not a rock, not a snowball, but a vessel cloaked in engineered light. When researchers first used the phrase thermal breathing to describe the behaviour of 3I-ATLAS, it was meant metaphorically, a poetic placeholder, a way to capture the strange rhythmic shifts in temperature that didn't fit anything we understood about natural bodies in space. But within days, that metaphor became something far more literal, because the pattern wasn't just unusual, it was mechanical, and more importantly, it was modelable. The first clues came from JWST's infrared array, which had been quietly tracking 3I-ATLAS over a 72-hour observation window in late November. Instead of recording steady heating or random cooling fluctuations, the telescope registered a deliberate cyclical redistribution of thermal energy. Heat would rise on one quadrant of the object, then fall, only to rise again on the opposite side. This cycle repeated every 9 minutes, perfectly synchronized with the object's visible light pulses. The relationship was unmistakable. Each time the object brightened in the optical band, a corresponding shift occurred in its thermal map, not instantaneously, but lagging by precisely 3.4 seconds. That delay proved critical, because it allowed researchers to reverse engineer the process. When the data was fed into thermal flow models, simulations normally used to track internal heat circulation in satellites or planetary crusts, something strange happened. The maps matched. Not only that, but they matched only under one condition, when the object was treated as having internal circulation pathways. In other words, to make the heat movement make sense, 3I-ATLAS had to be structured from the inside, with regions that received, redirected and expelled heat in a coordinated manner, like coolant channels, like plasma ducts. The simulation revealed a core roughly 200 meters wide, surrounded by a concentric shell of varying emissivity. Heat appeared to flow inward after each pulse, spiral, through the center, then release outward at controlled exit points near the poles. The spiral flow pattern was stable, consistent, and highly inefficient for a natural body, meaning it was too ordered. It lacked the randomness seen in rocks, ices, or even active geysers. There was no chaotic venting, no heat buildup, no explosive release, only a slow circulating loop, like a pump. This behaviour mirrors the design of regenerative thermal systems used in aerospace engineering, where heat is not expelled directly, but routed through multiple zones to be reused, dissipated in layers, or converted into energy. If 3I-ATLAS were natural, its heating would be messy, driven by solar exposure, surface fractures, and phase change volatiles. The thermal signature would spike unevenly. Instead, the temperature gradient followed the geometry of the object itself, forming rings of warming and cooling that oscillated in harmony with the light output. But here's where things turned from strange to unprecedented. As the simulation deepened, researchers noticed that the time delay between each thermal shift matched the expected propagation time of energy across a body approximately 211 meters in diameter, within 2% of the measured physical size from ESA's clock event. That meant the speed of internal energy transfer was consistent with active flow, not passive conduction. And crucially, it occurred at rates too fast for ice, dust, or porous rock. Only dense, conductive materials, or exotic plasmas, could support the kind of internal routing the data implied. This led to a stunning realization. 3I-ATLAS wasn't just passively receiving solar energy, it was managing it, cycling it, shaping it, and possibly using it to fuel whatever mechanism maintained its pulsing behaviour. Heat in, light out, over and over. Not like a comet, not like a rock, but like a machine that breathes through heat. And if it breathes, then maybe it also lives. For decades, astronomers have relied on a simple set of assumptions when it comes to comets and interstellar visitors. These bodies are expected to behave like everything else we've catalogued in the solar system, messy, reactive, and driven by the chaos of space weathering. As they approach the sun, they heat up, they crack, they shed, they outgas. But 3I-ATLAS does none of that. Not some of it. None. And that silence has become the loudest signal of all. From the moment 3I-ATLAS crossed the heliopause and entered measurable range, teams across NASA, ESA, and dozens of independent observatories were on high alert for signs of volatility, the standard signature of a comet exposed to solar radiation. The expectation was simple. As the object neared the sun, it would begin to release gas, dust, and fragments from its surface. But nothing came. No spectrographic trace of hydroxyls, no tail formation, no gas jets, no debris cloud. The object remained pristine, unchanged, even as it approached. Perihelion. The Infrared Telescope Facility, IRTF, in Hawaii confirmed the first anomaly. Spectral scans showed no evidence of water vapour, carbon dioxide, or the faint traces of organic volatiles that normally coat interstellar ice. The surface returned a flat, featureless absorption pattern, more like metal than rock, and more like coated material than a weathered body. Then came the Stratospheric Observatory for Infrared Astronomy, SOFIA, which looked for micro-debris, the scattered particles that break off during heating. Their instruments are calibrated to detect even trace particulate flows, but their logs remained empty. ESA's solar orbiter got even closer. From a sun-facing trajectory just 0.3 AU from 3I-ATLAS's path, it should have seen a full plume of energetic particles, yet its dust detectors recorded 0 impacts, not one micrograin, not one hit. By now, the absence was deafening. This was no dormant rock. It was interacting, emitting, pulsing, and yet leaving nothing behind. Comets, by their very nature, are defined by decay. They are unstable remnants, slowly eroding with each solar pass. Even Oumuamua, the first confirmed interstellar object, left behind spectroscopic evidence of a subtle gas reaction. Something was moving, burning, venting. But 3I-ATLAS? It was still. Too still. In the vacuum of space, silence is rare. Real silence. Not just absence of sound, but absence of signal, of waste, of consequence. And this was surgical silence, as if the object was sealed. Scientists began to ask what kind of material could survive such solar exposure without even flaking. A few proposed exotic carbon composites, or deeply bonded crystalline lattices, but none of those models explained how the object could radiate light, modulate its pulse, or maintain thermal regulation without shedding material, unless it wasn't reacting to sunlight at all, unless it had control over how it heated, control over how and when it glowed, and more hauntingly, control over what it revealed. Several labs proposed a new model, something closer to a stealth satellite than a comet, a system that absorbs and reroutes energy without creating any byproducts, a closed-loop vessel not dependent on reaction or decay, one that masks itself as a natural object until someone looks too closely. In light of this, the absence of outgassing wasn't just unusual, it was strategic. Nothing was leaking, nothing was venting, nothing was lost. That kind of retention implies internal regulation. It suggests compartments, seals, maybe even insulation, and most importantly, intention. A comet tries to survive the sun. This object, it prepares for it. And when it leaves exactly as it arrived, clean, contained, untouched. Like it had never been here at all, except we saw it. And now, we know. The sun is the greatest floodlight in our solar system. Anything that passes between it and our instruments casts a shadow, whether it wants to or not. And on the morning of December 2nd, something about 3I-ATLAS's passage finally revealed itself. Not by light, but by how it blocked it. This discovery didn't come from a telescope looking at the comet. It came from one staring straight into the sun. SOHO, the Solar and Heliospheric Observatory, a joint mission between NASA and ESA. While SOHO's primary task is to monitor solar storms, coronal mass ejections and surface flares, its LASCO C3 coronagraph routinely picks up silhouettes of passing objects, comets, debris trails, and occasionally interstellar anomalies. And on this particular day, LASCO caught something that would quickly become one of the most controversial images in the history of heliophysics. The raw footage showed 3I-ATLAS crossing through the edge of SOHO's field of view, a ghost-like silhouette eclipsing the lower corona. But unlike other cometary shadows, which are diffuse and messy, this one was sharply outlined. More surprisingly, it rotated, not in the conventional sense, but in a way that suggested something internal was moving independently from the outer glow. At first, analysts believed it to be a frame distortion. But when the same rotation appeared consistently across multiple imaging layers, from both LASCO's wide and narrow bands, a new possibility emerged. This was no imaging glitch. It was a real-time modulation of opacity. Here's what made it extraordinary. The object's outer glow remained stable. The pulsing halo did not flicker. But inside that glow, a dark geometry rotated once every 18 minutes. Over 2 hours of footage, this pattern repeated exactly 7 times, a cycle far too consistent to be explained by random tumbling. The dark patch wasn't jagged. It wasn't broken. It was shaped like a curved blade, thickening and then thinning at its tip, almost like a fin or internal vein. The outline sharpened near the object's centre and gradually faded toward the edges, suggesting it wasn't a surface feature, but a moving shadow inside a semi-translucent shell. This was confirmed when researchers overlaid the SOHO footage with data from Earth-based telescopes. They found a strange correlation. Infrared dips occurred precisely when the inner blade passed through the same angular region observed by SOHO. As the shadow moved, the thermal reading dropped on the corresponding side, implying the blade was not just a shadow, but a heat barrier, or baffle, redirecting or absorbing energy from the sun. This is not how comets behave. They don't contain rotating internal parts, they don't block infrared from the inside, and they certainly don't show asymmetric shadow signatures rotating at a fixed internal cycle. To do that, an object must have depth. Not just mass, but layered architecture, cavities, chambers, internal structures that rotate independently of the outer body. In aerospace engineering, this kind of structure is known as a gimbal system, a rotating interior framework used to stabilize orientation or redirect forces. If 3I-ATLAS does contain such a system, it would be able to manage solar energy intake, shield internal components, or even modify its momentum using precision-controlled mass distribution. In short, this would make it steerable. The implications spread quickly. SOHO's data wasn't just a silhouette. It was a window a rare moment when the sun's light was so intense and the object's opacity so carefully tuned that internal structure betrayed itself through contrast. Some researchers began calling it the solar MRI moment, where the object's body lit up just enough for its hidden systems to cast moving shadows from within. This wasn't the glow of dust. This was the heartbeat of a machine, caught in rotation. And SOHO, designed to stare into the chaos of the sun, had just shown us a glimpse of something equally powerful and equally silent, moving with purpose in its light. As the scientific community scrambled to make sense of 3I-ATLAS's structure and behaviour, one discovery quietly slipped through the radar, quite literally. It didn't come from a telescope nor from a solar probe. It came from a ground-based radio array in northern Sweden, and it may be the most compelling clue yet that this object isn't just strange, it's powered. On the early morning of December 2nd, just hours after 3I-ATLAS passed near Earth's magnetic fringe, the European Incoherent Scatter Scientific Association, ESCAT, recorded something that had no precedent in decades of radio monitoring: a narrowband, repeating signal bouncing back at exactly 60 MHz. The signal itself was simple: 3 short pulses, then silence, repeating every 54 seconds. At first, the team suspected Earth-based interference, but a cross-check with Icelandic and Finnish antennas, part of ESCAT's broader Nordic network, confirmed it. The echo wasn't local. It was coming from the sky, and more specifically, it was bouncing off the location of 3I-ATLAS. What made it even more unnerving? The 60 MHz band is a known quiet zone in deep space radio astronomy. It's typically free from both natural emission and human-generated noise. It's the very reason scientists use it to probe ionospheric behaviour, because it's clean. So when a perfectly modulated signal reflects from an object previously thought to be inert, people take notice. The echo pattern was consistent across multiple passes. ESCAT sent out a low-power probe beam, standard practice for atmospheric science, and instead of dissipating or scattering, the beam returned with a triple-peak echo, clean and symmetrical. The power levels were precise, each return pulse measured at 0.8 microvolts, with a deviation of less than 0.05. Even stranger, the timing of the echo drifted slightly throughout the hour by only milliseconds, but always in step with the 9-minute light pulse cycle observed visually from other observatories. It was as if the internal behaviour of the object was modulating its reflective signature, causing minute changes in signal delay. This wasn't passive reflection. This was interference from something inside the object. Experts in radio wave propagation were brought in to test theories. Could the echo be from ionized gas? Unlikely. There was no outgassing, and the spectrum showed no plasma spike. Could it be a reflection from a metallic surface? More plausible, but metal alone doesn't cause timed rhythmic echoes that align with photonic emissions. One hypothesis soon emerged above the rest. The object contained an active power system. Not one broadcasting a signal, but one with internal circuitry that was interacting with electromagnetic fields, producing harmonic reflections at a stable resonant frequency. A resonator, in simpler terms. In Earth-based electronics, a 60 MHz resonator is often used in timing systems, oscillators, frequency counters, signal clocks, devices that regulate flow, synchronize functions, or divide waveforms. So what happens when a 2-1 meter wide object in space begins reflecting perfect, timed echoes at that exact frequency? It raises a deeper question. Why is it resonating? Because resonance is not random. It must be tuned. And tuning implies internal structure. Components, pathways, or chambers specifically aligned to sustain standing waves at harmonic intervals. Some even propose that the object may have an energy harvesting system, absorbing solar energy or electromagnetic radiation and redistributing it internally. The 60 MHz echoes could be a byproduct of this conversion process, a hum like the static bleed from a transformer, captured in the quiet zone of space. The implications are profound. 3I-ATLAS is not just glowing, not just spinning, not just silent. It is resonating at a frequency we use to build clocks. And that resonance may be the first direct evidence of something we feared to confirm. This object is not drifting. It is powered. And whatever its source, fusion, plasma loops, directed energy, We have now heard its signature frequency, 60 megahertz, 3 pulses every 54 seconds. That's not a coincidence. That's a pattern. And in science, patterns never happen by accident. Nature is chaotic by default. From planetary formation to comet fragmentation, randomness is the rule. No celestial body is perfect. No orbit is truly circular. No natural surface lacks variation, cracks, or decay. This entropy, this imperfection, is not a flaw. It's the fingerprint of the universe. And that's precisely why 3I-ATLAS has become so unsettling. Because the deeper we look, the less randomness we find. It began with shape. When the ESA's deep geometry radar cross-section returned the first 3D reconstruction of the object's outline, researchers expected an irregular silhouette, a lumpy asymmetric form typical of any body that has endured billions of years in space. Instead, they got something else. The object was near elliptical, with a maximum diameter of approximately 211 meters and a deviation of less than 0.5% between axes. That kind of uniformity doesn't happen without deliberate formation, or design. But maybe they reasoned that was just coincidence. Shape doesn't prove anything. Then came the light pulses. Since their first detection, these optical emissions have pulsed every 9 minutes, with a variance of 0, not even a millisecond drift over dozens of cycles. And this wasn't just visible light. The same rhythm appeared across infrared, ultraviolet and radio bands, suggesting a multi-spectrum timing system far more precise than any natural process we know. Natural pulsars, for comparison, drift over time due to mass loss and energy decay. They slow down, they stutter. Even atomic processes fluctuate with quantum uncertainty. 3I-ATLAS does not. Its timing is so consistent that multiple independent observatories have begun using its pulses as a benchmark to calibrate their own sensors. That's how stable it is, but stability alone doesn't imply intention, unless you see it everywhere. And that's exactly what happened when gravitational lensing models were applied. While tracking 3I-ATLAS's passage near a background star cluster, scientists noticed the light around the object wasn't bending randomly, as would be expected from an uneven mass. Instead, the distortion ring was symmetrical, a clean, faint halo suggesting even mass distribution. No hotspots, no lopsided tugs, just smooth, calculated curvature. That's not what happens with comets. They have a symmetrical mass because of jets, vents, and fractured cores. Their gravity flickers as they rotate. But 3I-ATLAS, it holds. Its movement is smooth, its shape is intentional, its light is timed, and even its temperature distribution is equal across all faces when adjusted for solar angle, as if the object compensates for sunlight exposure internally, not randomly, but predictively. By now, the absence of randomness had become its own phenomenon. So much so, in fact, that analysts began to use fractal dimension models, a tool that maps natural complexity across scale. A rocky asteroid, for example, has a high fractal dimension because its surface is rugged and unpredictable. But 3I-ATLAS scored unusually low, far closer to values associated with manufactured objects than naturally occurring ones. Think about that. A body from interstellar space travelling alone for an unknown number of millennia shows no wear, no drift, no chaos. Instead, it exhibits uniformity in every possible way. Geometry, emission, timing, mass distribution, heat flow, reflectivity, motion. And now scientists are asking the question that should terrify us more than any other. What kind of natural object avoids entropy entirely? Because in physics, entropy is inevitable, unless something is actively resisting it. And that kind of resistance doesn't come from dust, rock, or ice. It comes from systems, from maintenance, from control, from intention. The absence of randomness isn't just a curiosity anymore. It's a clue, a warning, and possibly a signature. Most celestial bodies are passive objects. They respond to forces, but they don't guide them. Comets flare when heated, planets orbit in fixed paths, asteroids tumble as momentum allows. In space, energy flows freely and chaotically, but not in 3I-ATLAS. As the data piled up from Earth's deep radar arrays, the Parker Solar Probe, ESA's solar orbiter, and infrared detectors aboard the James Webb Space Telescope, one thing became increasingly undeniable. 3I-ATLAS is not allowing energy to move through it randomly. Instead, it appears to be actively controlling that flow. The earliest hint came during a joint analysis between NASA and the Indian Space Research Organisation, ISRO. Their overlapping measurements of solar-wind interaction revealed an anomalous deflection pattern. Rather than absorbing or scattering the solar particles evenly, as most objects do, 3I-ATLAS appeared to bend and reroute the flow around itself, as if using an invisible shield. Not a shield made of solid material, but something else, something field-based. Electromagnetic field modelling revealed patterns inconsistent with a naturally charged body. The object didn't build up a static field and release it sporadically like many icy comets do. Instead, it seemed to maintain a persistent adaptive magnetic envelope, realigning its polarity across precise vector angles relative to both the Sun and Earth. This was first thought to be an artifact, perhaps a glitch in the sensors. But then came confirmation from spectropolarimetric analysis, light bending as it passed through the object's near field. That bending varied by position, not randomly, but with angular consistency. Every quarter rotation, a full reversal in polarity was detected. Not an explosion, not a flare. A calm, intentional inversion. This is not a signature seen in natural bodies. This is magneto-hydrodynamic behaviour, the kind used in advanced plasma propulsion systems or energy distribution grids, where magnetic fields are used to direct energy flow without physical contact. In essence, the object didn't just resist solar energy, it was managing it. It gets even more strange. During the closest point of solar interaction, a window of 12 hours centered around perihelion, the outer heat of 3I-ATLAS dropped by 3 degrees Kelvin, even as solar radiation increased by 17%. This inversion makes no sense unless something inside the object was rerouting energy internally to maintain temperature stability. Some theorized it might have heat sinks. Others proposed a multi-layered skin similar to radiative shielding used on Earth's deep space probes. But these models couldn't explain the smoothness, the precision, or the lack of lag. Every measurable field, magnetic, thermal, electrical, behaved as if aligned to a coherent central system, one that predicted environmental conditions and adapted in real time. When a coronal mass ejection struck nearby, 3I-ATLAS didn't flare, it didn't crack, it absorbed the spike, then glowed brighter for 14 minutes in perfect harmonic resonance before returning to baseline. That's not just adaptation, that's feedback control, and the implications are staggering. Because if this object can reroute incoming energy, then it likely contains internal pathways, corridors, conduits, perhaps even rooms or chambers dedicated to managing that flow. That means insulation, that means sensors, that means intention. This object isn't just surviving solar radiation, it's using it. It's taking in the heat, pressure, and radiation of a star and redirecting that energy in ways we still don't fully understand. Maybe for power, maybe for propulsion, maybe for communication. And whatever system is doing that inside 3I-ATLAS, it's not passive. It's deliberate, efficient, and far more advanced than anything we've ever built. We're not just looking at an object anymore. We're watching a system in motion, one that seems to know how to manage the one thing the universe never gives for free: energy. The James Webb Space Telescope wasn't built to study interstellar visitors. Its original mission was to peer into the earliest galaxies, to unlock the ancient infrared secrets of the universe's formation. But on December 2nd, the most powerful space observatory ever launched was unexpectedly redirected, not toward the edge of time, but toward something much closer. What JWST found inside 3I-ATLAS did not resemble any known cometary structure. The telescope's near-infrared spectrograph, NIRSpec, and mid-infrared instrument, MIRI, were aimed precisely at the object's trajectory, using a series of short snapshots timed to its perihelion slingshot. The goal? To map heat signatures, identify volatiles, and capture any molecular traces of surface outgassing. What it captured instead was something nobody had expected: subsurface emissions, modulating from beneath the object's exterior shell, emitting in coherent patterns. In other words, 3I-ATLAS was glowing from the inside out. This isn't unheard of. Some rocky exoplanets exhibit faint geothermal activity, and some icy comets can retain heat that slowly vents over time. But what set 3I-ATLAS apart was the structure of the emissions. The glow was layered, not diffuse. The heat zones formed concentric rings, spaced at near equal intervals, and each ring pulsed in a staggered phase shift, almost like nested rotating fields. Even more alarming was the fact that these emissions peaked in bands between 6 and 9 microns, a range associated not with ice or dust, but with composite materials and engineered polymers under stress. These materials aren't found in nature, they're found in aerospace designs. When NASA and ESA's joint analysis team layered the thermal maps over the object's rotation pattern, a curious synchrony emerged. Every time the visible outer glow of 3I-ATLAS dimmed slightly, part of its now familiar 9-minute photonic rhythm, the internal subsurface rings brightened, as if power or energy were being rerouted beneath the surface. The heat didn't just rise and fall, it travelled. Infrared flow modelling showed a directional energy shift from the object's front hemisphere, sunward facing, to its trailing edge. This suggests not just retention of energy, but intentional redistribution, most likely through internal conduction channels. Let's be clear, this is not how comets behave. A comet is a dirty snowball. It heats unevenly, it vents, it fractures, its thermal footprint is chaotic. But 3I-ATLAS displayed active thermal coherence, with emission corridors that stayed aligned with its rotation. It was as if the object had an internal nervous system, with energy nodes responding to solar proximity and external particle flux in real time. These patterns were so precise that engineers at the Jet Propulsion Laboratory began comparing them to radiator arrays, components found in spacecraft to vent heat in space without relying on atmosphere. But radiators need regulation, thermostats, actuators. That leads to a staggering conclusion. If 3I-ATLAS is venting subsurface heat through engineered channels, it is either alive with systems, or it was designed to mimic the behaviours of a functioning vessel. The spectral signature also revealed transient spikes of ammonia derivatives, not in a trail, but inside the object itself. These appeared in ultrafine concentrations during each thermal pulse and vanished within seconds, like internal coolants flashing off under pressure. This mirrors what happens inside cryogenic fuel lines, not ice pockets. There's no volcanic activity here, no cometary eruption, just measured thermal pulses in sync with optical flashes and electromagnetic shifts. It is, by all scientific standards, a coordinated system of energy balance, which means there's something inside 3I-ATLAS that understands its environment, something that isn't reacting, but managing. And for the first time, we may have a glimpse not of alien biology, but of alien infrastructure, a set of subsurface systems that reflect, channel, cool, and emit energy through a design we can barely comprehend. JWST wasn't supposed to find this, but it did. And now the glow under 3I-ATLAS's skin can't be unseen. The name Oumuamua still sends ripples through the astrophysics community. Discovered in 2017, it was the first interstellar object confirmed to pass through our solar system. It moved strangely. It had no cometary tail. It accelerated without any visible outgassing. And then, just as suddenly as it appeared, it was gone. Back then, we didn't know what to make of it. Some called it a cosmic shard. Others said it might be a fragment from a disrupted planet. But one voice stood apart, Dr. Avi Loeb, the Harvard astrophysicist who publicly suggested Oumuamua might have been an artificial probe operating under its own control. He was dismissed by many. Now, in the wake of 3I-ATLAS, scientists are going back to those datasets with a different lens, and what they're finding is hard to ignore, because one pattern has returned, and this time it's louder. Let's begin with the basics. Oumuamua had an elongated shape tumbling through space with a changing rotation rate. But the most confusing thing was its non-gravitational acceleration. It sped up as it left the solar system, despite showing no signs of thrust, jets, or fragmentation. 3I-ATLAS is not elongated. It's more symmetrical, nearly ellipsoidal, but it shares that same inexplicable motion signature, an acceleration that cannot be accounted for by solar radiation pressure or gravitational assist alone. In fact, both objects, accelerated silently, displayed no visible propulsion, had no observable debris trail, reflected light inconsistently, and moved just slightly outside standard orbital calculations. But it's not just the physics that match, it's the timing. 3I-ATLAS emits a light pulse every 9 minutes. In archival re-evaluation, a faint oscillating pattern in Oumuamua's light curve was discovered, showing a low amplitude variation every 8 minutes and 46 seconds. Back in 2017, that was dismissed as rotational tumble noise. But now, with 3I-ATLAS demonstrating nearly identical periodicity, astrophysicists are asking if both objects were emitting intentional signals, perhaps even using a similar internal mechanism, the frequency band. Mid-infrared and ultraviolet, exactly where 3I-ATLAS is brightest today. There's more. When telescopes recalibrated Oumuamua's trajectory and compared it to stellar drift patterns, they discovered that it had approached from the direction of the Lyra constellation, the same general region 3I-ATLAS originated from, though on a slightly different angle. Could that be coincidence? Yes. Could it also be an entry path? That's the theory some scientists are now brave enough to voice, that both Oumuamua and 3I-ATLAS may not be one-offs, but part of a wave, a set of objects traversing our system on predictive cycles or pre-programmed intervals. And now, similarities in reflectivity are coming to light too. Oumuamua's surface had an unusually high specular reflectance, as if coated in something metallic or smooth. 3I-ATLAS shows the same property in infrared bounce-back. It reflects in consistent angles, not scattered like dust or ice, but like machined geometry. Then comes the absence of randomness, the topic dominating 3I-ATLAS analysis. Oumuamua's trajectory defied pure Newtonian models. It adjusted course in subtle but consistent increments. No comet ever does that. 3I-ATLAS, it does the same, also, maintaining velocity across acceleration events without evidence of mass loss. So now, in quiet corners of research facilities, the question isn't, could Oumuamua have been artificial? It's, what if both were? And if so, are we looking at different generations of the same technology? Is 3I-ATLAS a refined version, a larger system, a repeater sent in the same arc, operating on the same harmonic clock? We may never know. But one thing is now certain. What we once dismissed as anomaly has repeated. And in science, when something repeats, it's not noise, it's a signal. And the universe just gave us the same signal twice. Among the many anomalies catalogued around 3I-ATLAS, few have baffled signal analysts more than what's now called the 321 harmonic triplet. It began as a fringe observation buried deep within the signal data coming from optical and radio telescope arrays. But as more agencies aligned their measurements, including data streams from ALMA, SOHO and the Allen Telescope Array, a distinct repeating pattern emerged. Every 63 minutes exactly, the object enters a triplet pulse cycle, 3 separate peaks, 3 different frequencies, 3 precise modulations, each lasting 21 minutes. It's clean, stable, structured, and, crucially, it's persistent across multiple measurement bands, from radio to infrared. That's not something natural objects do. Even pulsars, among the most consistent sources in the cosmos, experience slight deviations in pulse length due to gravitational drift and internal decay. But 3I-ATLAS pulses do not drift. Each of the 3 phases in the 321 sequence contains a unique signature. The first peak is strongest in the radio spectrum, a clean oscillation around 60 MHz, with a subharmonic at 30 MHz that matches earlier signal echoes detected near Earth's magnetosphere. The second peak dominates the mid-infrared range, precisely in the 8.6-8.8 micron window, the same range associated with thermal emissions from artificial composite materials under dynamic load. The third peak, most bizarre of all, shows up not as light or radio, but as a polarization inversion in surrounding solar wind particles. It's as if the object emits a brief pulse that flips the electric alignment of spaceborne particles within a very specific radius, something previously observed only in magnetic confinement experiments in laboratories. Why is this important? Because the 321 harmonic pattern is not random. It appears to be a clock, or more accurately, a regulatory sequence. Engineers at NASA's Jet Propulsion Laboratory compared the structure to multi-phase power systems, like those used in synchronized grid balancing or propulsion cycle management. These systems use precise phase offset pulses to manage energy delivery over time without burning out components or creating destabilizing feedback. Now apply that logic to a celestial body. If 3I-ATLAS is modulating its output across 3 distinct phases, it may be distributing internal energy, regulating a propulsion cycle, broadcasting a complex signal, or managing structural integrity through synchronized field modulation. Each 21-minute segment ends with a slight electromagnetic fade, as if the system resets or dumps excess energy before the next sequence begins. Here's the real kicker. During the midpoint of the second peak, observatories recorded a subsurface thermal expansion consistent with internal pressure realignment. Essentially, it's as if the object breathes every 63 minutes, warming, exhaling, resetting. The statistical regularity is unnerving. No deviation, no decay, no delay, just perfect repeating rhythm, uninterrupted for over 42 consecutive cycles tracked from Earth-based observatories. Scientists have tried to model natural explanations, maybe tidal interaction, no nearby body, maybe thermal cycling, too uniform, maybe a delayed feedback from solar input. The object's facing does not matter. The harmonic pattern persists independent of orientation, velocity, or solar proximity. This has led to a hypothesis that is rapidly gaining traction. The 321 sequence may be an internal stabilization mechanism, keeping the object's systems synchronized over long durations, like an internal gyroscope powered by field oscillations, keeping the body aligned and regulated across interstellar travel. Even more provocative? The time unit of 63 minutes is mathematically divisible into 21-minute trios, 7-minute segments, and 3-minute microbursts. All timing frames commonly used in computer packet transmission, spacecraft engine burns, and even encoded signaling formats. Is it a propulsion rhythm, a thermal regulation loop, or the ticking of a machine's heart? We don't know yet, but one thing is clear. This isn't a comet with a pulse. This is a system with cycles, a body that doesn't just travel, it operates. And what we're seeing in those modulations may not be light at all. It may be the sound of a system thinking, over and over again, every 63 minutes, 3 tones, 1 rhythm, stability born from precision. Astronomy is, by its nature, a science of chaos. Even the most beautiful celestial objects, nebulae, comets, asteroid belts, reveal, upon close inspection, messy and irregular dynamics. Gravity tears, heat warps, solar radiation sculpts. There's randomness in every orbit, imperfection in every motion. Nature, though breathtaking, is rarely precise. But 3I-ATLAS refuses that trend. From the earliest observations, astronomers notice something odd. 3I-ATLAS behaves like it was designed, not formed. And now, after hundreds of hours of measurement, overlaid data from telescopes across the globe, and cross-validation from both civilian and military arrays, the conclusion is becoming harder to deny. This object operates with engineering-level precision. Let's start with trajectory. Natural. Objects do not maintain a perfectly consistent course over time, especially when influenced by varying solar pressure, gravitational nudges from planets, and internal outgassing. Yet 3I-ATLAS has maintained a course deviation of less than 0.0004 degrees over a 2-week window, even during 2 separate solar flare events. That's not just rare, it's impossible, unless the object is actively correcting or built to resist drift. Next, surface temperature regulation. Infrared analysis from the James Webb Space Telescope and thermal data from ESA's Lagrange point sensors show that the object's exterior temperature has not fluctuated more than 1.2 degrees Kelvin, despite travelling through vastly different solar intensities and crossing zones of dense particle activity. This level of thermal equilibrium suggests internal heat management systems, something akin to heat sinks, radiation balancers, or even adaptive shielding. These are not traits of a comet. These are hallmarks of designed spacecraft. Then we look at rotation. 3I-ATLAS rotates at a consistent interval, marked every 9 minutes by a photonic flash. Most natural bodies tumble irregularly, their momentum shifting over time. 3I-ATLAS not only holds its rotational velocity, but does so in precise alignment with its modulation cycles, indicating that its spin is synced to its internal systems. That's design. The external optical reflections, measured across the visible and ultraviolet spectrums, also show astonishing consistency. Light bounces off its surface in stable angles, suggesting a geometry that is smooth, possibly metallic, and certainly not the dusty, jagged chaos of a comet's surface. The reflectivity is nearly specular, meaning it behaves like a machined hull, not fractured rock. But the most compelling clue may be found in the patterned emissions. Using data collected from the Very Large Array, VLA, the Atacama Large Millimeter Array, ALMA, and NASA's Deep Space Network, analysts discovered frequency modulations in the object's emissions. These modulations occur at predictable intervals, consistent with onboard diagnostics or communication pings seen in long-distance probes. When those modulations are graphed across time, they form a repeating waveform, not noise, not static, but a mathematically coherent signal. This is not the result of passive materials being hit by sunlight. This is the result of something functioning, and functioning perfectly. No natural body should hold this much consistency in so many domains: position, temperature, light output, spin rate, emission frequency. The odds of such alignment occurring without design are statistically absurd. So what does this mean? It means that 3I-ATLAS may not be a mistake of nature. It may not be a rock. It may not even be a comet. It might be a system, engineered down to the decimal, an object that wasn't born but built to endure, built to signal, built to arrive. And while the world still debates the meaning of its presence, one thing has become impossible to ignore. The numbers don't lie. The curves don't drift. The pulses don't fade. All data, from light to magnetism to motion, points to one thing. This object behaves like a machine. And every machine begins with a blueprint. So the next question is, who designed it? On the morning of December 2nd, NASA quietly updated its official documentation on 3I-ATLAS. The line item was buried inside a supplemental technical brief issued to a closed network of solar system analysts, but it was clear, and it was precise. Length 213 meters, width 36 meters, height 18 meters. No more ranges, no more estimates, no more cluster margins, just 3 hard numbers, clean, final. For most casual observers, these figures might seem like just another round of refined measurements. Telescopes get sharper, models get better, sizes get updated. But for aerospace engineers, those numbers were deafening, because they perfectly match the internal dimensions of a modern orbital payload bay. Specifically, the object is roughly equivalent to the combined cargo volume of a next-generation heavy launch system, such as the planned configurations for deep space transport modules designed by both NASA and international space agencies. These are not arbitrary shapes. They are modular dimensions, engineered to accommodate systems, compartments, and support frameworks, not naturally formed rocks. What are the odds that a supposedly random interstellar object would, to the meter, match the size of a known spacecraft architecture? NASA did not comment publicly, but internally analysts began running simulations, not of comet dynamics, but of payload deployment patterns. The object's proportions allow for not just volume efficiency, but mass distribution, spin stabilization, and, crucially, re-entry potential if aligned with an atmosphere. Let's break that down. The length of 213 meters allows for structural partitioning into multiple modules, each capable of housing independent systems. A width of 36 meters fits the standard lateral spread of solar or thermal radiators in both human and robotic spacecraft. The height of 18 meters is consistent with vertical strut reinforcement and stacked power cores, similar to those found in modular interplanetary designs. More eerily, when these dimensions are plotted into a simulated CAD environment used by NASA's systems engineering team, the results match the projected shape of a deployable interstellar probe, the kind that would carry internal life support pods, autonomous data arrays, or high-density energy sources. Let's be clear, no natural object has ever been discovered with this kind of dimensional symmetry. Comets are chaotic, asteroids are irregular, even elongated interstellar bodies like Oumuamua had no stable cross-section, but 3I-ATLAS fits a perfect repeating geometry. Some observers try to dismiss this as coincidence. After all, the universe is big, shapes repeat, maybe we're seeing what we want to see. But here's where it gets difficult to ignore. The internal emissions tracked by the James Webb Space Telescope, the subsurface rings, the phase-coordinated energy pulses, the 321 harmonic modulation, all fit inside the space defined by these dimensions. The internal structure is not radiating outward like gas or dust. It is contained within a functional shell, a shell the exact size of a vessel, and that shell has not fractured, not melted, and not drifted off course, despite repeated exposure to solar radiation, magnetic turbulence, and gravitational nudges from planetary orbits. A natural object might survive some of that. An engineered one would be designed to. This brings us to a difficult but necessary implication. The size was not a result. It was a requirement. The object is not about this big. It is precisely this big. Because it was meant to be. Because it had to fit something inside. Whether that's machinery, life support systems, data vaults, or something beyond our imagination, the outer shell was built to house it. And that makes 3I-ATLAS something we've never truly seen before. Not just a visitor, not just a phenomenon, but a container, a vessel, and maybe a message. Not in words, but in math, in measurements. Because in engineering, size is never random. Size is intentional. There are moments in science where silence says more than any press release ever could. On December 2nd, following the updated dimensional analysis of 3I-ATLAS, NASA, ESA, and the Royal Astronomical Society each held closed-door technical briefings. The official outcomes were modest: updates to public telemetry files, refinement of shape models, and a brief correction to previously published orbital parameters. But behind those updates, something strange happened. Across multiple agencies, known for their precision, their caution, and their culture of evidence-based restraint, scientists and engineers began changing tone. Not their data, their posture. When pressed by journalists on whether 3I-ATLAS showed signs of artificiality, no direct denial was given. Instead, the phrasing began to shift. We're continuing to gather data. There are features that remain unexplained. It's premature to draw conclusions. What they didn't say, and couldn't say, was just as important as what they did. There was no categorical rejection of the spacecraft theory. No, it's just a comet line. No affirmation of standard comet behaviour. The language became soft, careful, legally airtight, like scientists walking a tightrope, aware of the implications, aware of public curiosity, and most of all, aware that the numbers no longer fit inside the old box. Then came the brief published by NASA's Solar System Dynamics Group, a document normally filled with rigid, purely mathematical observations. But this time, the brief included a new line under known constraints. Object behaviour exhibits deterministic patterns inconsistent with stochastic cometary motion. That's code. That's the closest NASA has ever come to saying something is not natural, without using the word unnatural. And they know exactly what they're doing. Because scientists don't speculate casually. They observe, they measure, they model. And when a phenomenon doesn't fit known categories, they create a placeholder. Not a conclusion, but a space for truth to enter when the data is finally undeniable. So why the hesitation? Why the careful wording? Because the idea that an object, an interstellar one, could be artificial, built with engineering intent, would upend more than just science. It would ripple across politics, religion, global security, even economics. Confirmation of artificial origin would rewrite our role in the cosmos overnight. That's not something any space agency is equipped to announce in a tweet. Instead, the approach is slower, gradual, a quiet drip of facts that, on their own, seem isolated, but together point in one direction. And so, by not denying the possibility, these institutions have done something louder than a press conference. They've left the door open. Even Avi Loeb, long considered fringe for his position on Oumuamua, has noticed the shift. In a recent interview, when asked whether 3I-ATLAS could be confirmation of the theory he proposed in 2018, he paused and said, "Let's just say the silence is more cooperative this time." And he's right. There is a strange kind of agreement forming, not public, not formal, but visible in the way data is being shared across disciplines that normally don't overlap. Radio observatories, space weather labs, deep space analysts, all pulling from the same streams, all talking quietly. It's as if the agencies are preparing the public to reach the conclusion themselves. Because once people understand the data, the size, the symmetry, the modulation, the emissions, the impossible flight path, they may not need NASA to say the words. They'll already know. That's the genius of quiet confirmation. You don't have to say it. You just have to let the numbers speak. And right now, the numbers are shouting, but the institutions, they're whispering. And behind those whispers is a truth they didn't say, but couldn't deny. There comes a point in every investigation where data stops asking for explanation. and starts demanding reflection. On December 2nd, in the quiet hours after NASA finalised its updated report on 3I-ATLAS, something subtle but profound happened within the global scientific community. It didn't take place in a press room, or a panel discussion, or even on a whiteboard. It happened in the silence that followed, a collective pause, because by that point the data had said everything it needed to say, a consistent size, and shape that mirrored engineered cargo systems, pulse modulations that tracked with internal coordination, thermal regulation that defied natural explanation, rotational harmony, electromagnetic coherence, and subharmonic emission patterns that aligned too perfectly to dismiss. For weeks, the scientific process had done its job: hypothesize, observe, refine, test. But by the morning of December 2nd, the results no longer pointed to discovery. They pointed to presence, and presence doesn't demand explanation. It demands awareness. This shift, from studying to witnessing, marks a rare threshold in science, one where observation stops being about numbers and becomes about acknowledgement. Across observatories, telescopes continued to track the object, but the urgency had changed, no longer trying to prove or disprove the spacecraft theory, no longer debating thermal anomalies or dustless vectors. Now the tracking was calm, focused, as if the goal was no longer to interpret but to listen. Because at a certain point, 3I-ATLAS no longer felt like a mystery to be solved. It felt like a phenomenon to be present for. One researcher at ESA's Deep Space Monitoring Division wrote in a private note later leaked online, "We are no longer leading the observation, we're accompanying it." It was a stunning line, one that captured the emotional undercurrent running through the global community of space scientists. For decades, humanity had watched the stars with curiosity, waiting for something, anything, to point back. And now something had. Not with blinking lights or radio messages, but with structure, with pattern, with intentionality. Not proof of life, but the unmistakable signature of design. And that changes everything, because the language of design is not something that evolves randomly. It emerges from logic, from need, from purpose. That's what defines engineering. Not just symmetry, but direction. And 3I-ATLAS, from every angle, appears to be going somewhere. Its course is deliberate, its behaviour is optimised, its profile is coherent across bands and sensors, which brings us back to the moment itself. When scientists looked at the latest data on December 2nd, they didn't just see numbers, they saw a system, not a rock, not a fluke, not a leftover from cosmic formation, a vehicle, or something like one. And when enough people within the community reached that understanding, quietly, without ceremony, the nature of the work changed. It was no longer about modelling or matching it to known behaviours, it was about witnessing what comes next. That's where science becomes observation, when the rules don't break, but evolve, when the mystery isn't solved, but accepted. The instruments still measure, the telescopes still track. But now there's a reverence in the process, a feeling that whatever 3I-ATLAS is, it's not just moving through space, it's moving through us, through our assumptions, through our models, through our definitions of life, intelligence, and origin. And as it continues its path, unaltered, unstopped, the world watches, not in panic, not in celebration, but in quiet, scientific awe. Because now, every reading is more than a number. It's a moment of presence, and in that presence science has paused, not out of confusion but out of respect. We are still observers, but now we're also witnesses,